Hi and welcome to example 2 of internal resistance, and this is an interesting example. It combines some mathematical knowledge with internal resistance in a circuit. Here we've got our circuit given. Okay, they tell us the circuit consists of a cell, okay, of EMF E. So the EMF of this cell is given here, just as E. So remember, EMF is the total voltage that the battery can possibly supply, and it's probably what's printed on the packaging of the battery as well. They just give it as E, and an internal resistance of R. So R just represents, there is the internal resistance. A is a voltmeter, a voltmeter is placed across a variable resistor. Now what a variable resistor is a resistor that we can change its resistance as time goes by. So for example, the switch on your television or computer or whatever that increases the volume of the laptop or computer or television, that is a variable resistor. It is something that we can change its output energy of, and this is a variable resistor which can be set to a known value R. So the external resistor, we can change its resistance, and we know what that resistance is. So for example, it is a knob, and we can show it has 0 ohm, or so let's do it like that. Okay, 0 ohm or 5 ohm or whatever. We can change its resistance as we turn that knob. That's just an example. The equation used by the learner is the following. And sorry, I noticed I did not paste in the introduction to this question. It's an experiment the learner wants to use to determine the internal resistance of a cell. I do apologize. So that's what they're doing here, and what they do to get the internal resistance is they simply get a diagram, and they are going to use a variable resistor. They're going to change this variable resistor over time, and then just measure the output, the voltage across the variable resistor itself. Okay, so, and since it's the only resistor here, this voltage is equal to the total external voltage supplied, and this is what they find. Okay, so they plot their findings. So when the way that they plot it, they're going to use this equation here. This equation here, they take 1 over volts is equal to internal resistance divided by the EMF R plus 1 over the EMF. Now I can show you where that comes from. If we were to add these values together, we would have 1 over volts is equal to, add those two together, so I've got R over ER plus, and then 1 over this must get a capital R over ER, and then if we add this together, 1 over V is equal to R plus capital R over, oh sorry, this one requires external resistance. There we go. Okay, and now if we flip it around, we get voltage is equal to, and this is obviously the voltage meter reading over external, so this is the voltage over the load. The voltage over the load is equal to the EMF times R over total resistance. Total resistance. Now you'll notice this together, that's total volts divided by total resistance. That gives me total current. So the voltage over the load is equal to total current times external resistance. And that is basically where they get this from this from is they've expanded this in a different way, and the reason why they do that is because what they actually want to plot against each other is 1 over volts and 1 over resistance. So if we go and rewrite this just slightly, we'll get the following: 1 over volts plus, and I just want to rewrite it slightly. Instead of saying R over ER, I just want to say R over EMF times 1 over R plus 1 over E. Now the reason why I want to do that is so that I can have a gradient. Y is equal to mx plus c. So I want a gradient and a y-intercept. And the reason why I want that is because notice what they get when they plotted these values together. They got a straight line. These values almost fall perfectly on a straight line. Almost. Not perfectly, but almost. And now we can notice that this is my y-intercept. And I can calculate my gradient by just taking 2 points and using change in y over change in x. Typical math features that I'm using here. Okay, so let's start by saying write down the relationship of a mathematical relationship for the slope of the graph. And now you can see, well, this is what I wanted. Okay, the slope of this graph is given by the internal resistance divided by the EMF. Okay, use the information from the graph to calculate the EMF of the cell. So I just want E. Now how will I get E? Well, notice here that my y-intercept is just 1 divided by E. So my y-intercept here I can estimate is about 0,8. So 1 over E is about 0,8. So E, if I take 1 divided by 0,8, I'm flipping it around, 0.08, not 0, yes, 0.08, not 0.8, 0.08. Then I get 12.5, 12,5, and that is volts. That's the total volts supplied. Calculate the internal resistance of the cell. Now we have my, it shouldn't be an E like that. We have my E, and so we have that, and now I want lowercase r. Okay, internal resistance. Now you can see that is represented by the slope. So let's go and estimate the slope. Now when I will estimate the slope of a straight line, I usually try and find 2 points that I can be sure of the line passes through. Now there's not 2 that I can be sure of, and the further apart they are, the better. Okay, but it looks like it's passing through that point here. And what other point does it look like? Fairly confidently, I would say this one. Okay, you could say this one as well. Let's go for that one. It's a little bit further apart. Okay, so, and the reason why I do that is because I want change in y over change in x. So the change in y is I went from 0.6 to, what is this, 0.450, 6 minus 0.45 divided by, and then the change, that was the change in y. The change in x went from 7 to 10, so 10 minus 7. And so this is 3, and this is 0,15 divided by 3, which gives me exactly 0,05. This would be the slope of the graph. In other words, R over E is equal to 0.05. I've got ER over 12.5 is equal to 0.05, and so I can calculate my internal resistance as the product of those two. So that is a half of this is 6.25, so, and this is like 5 over 100, so I'm also dividing by 100, moving it 2, so that is 0.625 ohms. And there we go. It is quite a different type of question, not too difficult, but I hope you could follow me. So thank you very much for watching. We'll see you in another video.